All right, so here's number 10 of our practice problems. All right, so it says you have two masses, MA and MB, that are distance d apart. All right, so let's draw a little picture. So this is mass A, and this is mass B, and the distance is from their centers, just to let you know. So there's some distance d. And if that's the case, there's a force between them, the force of gravity. Isaac Newton was the one that first figured this out. The force of gravity, right? So this is the original force, is equal to it's a constant called the universal gravitational constant times the product of mass A times mass B divided by the distance between them squared. Right, so sometimes this is called an inverse square law, right? Because the the force depends on the inverse of the square of the distance. All right, so and by the way, this is an important idea. This inverse square law. Light intensity varies as the square of the distance as well. All right, so let's read this. All right, how does the gravitational force between the two masses change when the distance is doubled from the original distance? All right, and I've done A right here. It's so if you double the distance, uh, what happens is so if we call this the original force, all right. So I'm just going to keep the symbol F. All right. This right here is what I just drew. This is the original force. All right. So we're going to see in part A. All right. So you can do each one of these. They're done exactly the same way. You just basically varying the distance. All right. So for part A, if the distance is doubled, all right. So now we have this scenario, right, where we have the two masses, exact same two masses, but the distance is now, the new distance. Uh, I'll call the new distance R. R is equal to 2 times D. Two times the original distance. That's the idea. All right. And so if I redid the equation, right, it looks like this. F is equal to, big G times mass A times mass B. That's supposed to be an A. That's an A. Mass A times mass B, right? Those two haven't changed, but then divided by R squared. But see, if you so this is force in situation A. All right. So what we want to do is see how is that situation A related to the original. How is it related to this original force? All right. All right. Well, so all you have to do is plug in what R is. All right. So if we do that here, so here we go. The force when the situation is for A. I should have used different letters for the masses, but you get the idea. Hopefully, you get the idea. All right. So anyhow, this new situation, force A, when the two masses are twice the distance apart, that's all you've varied, is now going to equal G times mass A times mass B. Those are subscripts, by the way. They don't really look like that. Divided by so now instead of saying R squared, I'm going to put in the 2D. All right, so it's 2D, but you square that. All right, so that's the key. All right, and then see if I pulled the two out of this, this two squared, right? That becomes uh, G times mass A times mass B divided by D squared, but it's also divided by 4. But see, this right here is my original force, right? That's what this is. And so force A is equal to the original force, we'll call it F, divided by 4, right? Because see that there's the 4 right there, right? So in other words, when you doubled the distance, the force went down by a factor of 4. All right, and so you can keep doing this with these other with in situation B, right? Well, what would happen if you tripled the distance, right? So here let me see if I can erase this and do this quickly without making too much of a mess. All right, so all right, this is going to be situation B. All right, so here let's erase this real quick. It's just easier than. All right, so I'll do that. This is going to be B as best I can make it. All right, there we go. All right, so come back to this. Make sure this is right. I don't know why it doesn't. All right, so for situation B, all right, so now you see in situation B right here, the distance it triples the distance. All right, so now you put in the same thing. So here, this is if this was B, right? So let's cross that out. Let's consider this B. This is B. All right, so this is now going to be a 3, right? And then instead of a 4 right here, this would be 3 squared, right, or a 9, right? And so it would be the original force divided by 9. So that's and you see I have that right there. There it is. All right. In situation C, now what has happened in situation C here? Let me read it. The distance is reduced by 1/3. All right. So instead of this distance being d, it's d over 3, right? And so now I'd have to redraw the whole thing. But here, let me try to give you a sense of that. All right, so here. So and the rest of them are pretty much the same. So now if the distance, okay, so here's my two masses. I mean, they're supposed to be circles, whatever. This is A, this is B. So but now the distance or R, the new distance R is the original distance divided by 3. All right, so you just plug that all in, right? So the force, this is the force of what was this one? C, I think this one was C. All right, so the force C. Here, let me look real quick just to make sure I got that right. Sometimes I forget these things. Yeah, C is all right. So C is yeah, I got that right. All right, so let's plug this in. All right, so it's going to be big G times mass A times mass B. That doesn't change. Divided by, so now I'm going to divide by D over 3, right? So D over 3, but I've got to square that, right? And so now this, like if you look at this, you've got a fraction divided by a fraction, and so this becomes 3 squared times, G times MA times MB divided by D squared, right? So in other words, this now becomes 9 times the original force, right? So, but by bringing so when you bring them closer by a factor, they're now 1/3 their original distance. The force goes up by a factor of 9. All right, so that's the way that this works. All right, so that was problem number 10. All right, number 11 here is a modified version of Kepler's third law. It says the distance from the center of the Earth to the center of the Moon is 384,400 kilometers, and the period of the Moon is 27.4 3 days. Takes our moon to orbit the Earth. Find the mass of the Earth. All right, so there's the answer: 6 times 10 to the 24th. So the way that you do that, of course, is the modified version of Kepler's third law. Um, so it's 4 times pi squared times the distance between the two objects to the third power divided by big G divided by the period squared. All right, so the only trick is, I mean, it's not really a trick, but D has to be in meters, and the period has to be in seconds. All right, so that's the only thing. All right, so the distance is not hard to change. That's pretty simple. So it's going to be 3,384,400 kilometers. And so to change that, we know that in 1 kilometer there are 10 to the third meters. All right, so the kilometer part cancels, and that becomes 384,400. And you could just put 3 more zeros, or you could say times 10 to the third. And now it's in meters, and that's what you use. We're going to cube that in just a second. Now I have to convert the period from days to seconds. All right, so that's pretty simple. 27.3 days. That's a decimal point. 0.3 days, and I just say, all right, in 1 day there are 24 hours. In 1 hour there's 60 minutes. Remember, use MIN for minutes. That's an N, sorry. And then in 1 minute, there are 60 seconds. 60 seconds. All right, so here we go. And you can, so you just get out your calculator and let's figure this out real quick. All right, so here, let's clear this. All right, so the period would be here. Let me pause this. And so put all the numbers in times 60 squared, and so that's my period. All right, so that's the period. I'm going to put that into storage. So here, let's put that right there. All right, clear this. All right, and then so here we go. Let's see. I don't know if I have enough time. All right, so 4 times pi squared times this distance, which is 384,400 times 10 to the third raised to the third, and then divided by big G, which is 6.67 times 10 to the minus 11th equals, and then divided by the period, so that's going to be the memory recall, but then I've got to square that. All right, so there we go. All right, and that, even though it doesn't look like it, is the mass of the Earth. All right, so I'm going to argue that if you count, so the decimal point's right here. If you counted the decimals, that would be 6 times 10 to the 24th. All right, so the modified version of Kepler's third law gives us, yeah, I mean, look, watch. If I divide this by 1 times 10 to the 24th, I'll get 6. See, there it is. All right, so that's, of course, what the answer is. Oops, I didn't mean to do that. So the Earth is 6 times 10 to the 24th kilograms. So remember, with Blackboard, you would write that number like this. You'd write 6 and then an E24, like that. It shows you, it tells you about that in Blackboard as well. All right, so that's problem number 11. This is how we figure out these masses. You get orbital information, and then you can figure out the mass using the modified version of Kepler's third law. All right.